Let us look at this example. An object of mass m is thrown vertically up in the presence of air resistance. It then follows that the time of ascent, which is t1, is not equal to the time of descent, t2, full stop. Similarly, the initial speed u with which the body is thrown is not equal to the final speed v with which the object returns, full stop. Assuming that the air resistance is constant, show that the ratio of the two times, the time of descent and the time of ascent, is equal to this. F here is the air resistance. Also, that the ratio of the final velocity and the initial velocity of the object is given by this. And again, F here is the air resistance, G is the acceleration due to gravity, and M is the mass of the object thrown. So how do we solve this? The solution. First, let me tell us that this situation is describing a situation where there is resistance to the object that is in motion. For example, when the object is projected vertically upward, there will be air resistance. So again, there will be acceleration due to gravity. The direction of both acceleration due to gravity and the air resistance will be opposite to the direction of the motion. So like there are some kind of negative forces acting against the motion in this regard. But if the object is coming down, because we know that it will go up, it will get to a maximum height, then returns. So while coming down, the air resistance also will change direction. It's always opposing the direction of motion. But the weight of the body, which will be obtained by the product of the mass and the acceleration due to gravity, in this respect, is in favor of the direction of the motion. Let's use this diagram to explain further. We have the object. Assuming this is the object, it is vertically projected upward. It will go up, then it will turn because it will return downward like this. So the initial velocity is u, the final velocity is v. The height it has reached, this is the height it has reached. Let's call that height h. The height is h. And at the point where it has reached the highest height, the velocity there is 0. Let us call the velocity v1. It is 0 because it will stop temporarily before it turns and starts to return to the base. So v1 there is 0. As it is now, okay, before then, don't let us forget that the direction of acceleration due to gravity is usually downward. And then let us divide the motion into two parts for a better and easy to follow solution. The first is the first half, when the body is vertically thrown up, then it gets to the maximum point there. So that is upward motion. So that upward motion is something like this, where we have the object thrown up, and so it's going up. It gets to a maximum height, then it's about to turn, so it stops temporarily. V1 there is equal to 0 as shown up. The height is h. The height is h there. The initial velocity is u. Let me complete it with a dashed line showing that we are not actually looking at that for now. So with that, how do we get the force that is responsible for this motion upward? The force is obtained by the second law of motion. The second law of motion is saying that the mass mathematically is saying that mass multiplied by the square y by the t square is equals to the force that is responsible for the motion. Let me write it as F substrate E, showing that it is the effective force on the object. Then for this downward motion, we can re-express this to align with the problem at hand. The mass is m. The mass of the object is m. The acceleration while going up, let's say that is a1. The square y, the t square represent the acceleration a1. That is acceleration of the object while going up. Then this is equal to the effective force. The forces acting on it while going are two. The first one is the air resistance. Let's that be small letter f. And apart from that, we have the uh, we have the weight of the object, and the weight of the object is m multiplied by g. But in this case, both of them are negative. The weight of the object is usually acting vertically downward, and the air resistance while the object is going up is also acting vertically downward. So two forces are acting on it, but in the other direction of the motion. So we have F plus mg acting on it, but they are negative. They are negative. In this regard, we can make A1 the sort of formula, which is the acceleration of the object. That will give us minus F minus F divided by M1. M is M rather. M is M. Okay, so plus this will have gone plus G. Plus G. Let's call this one equation 1. Let's call it equation 1. So from here, if you look at the question, we need to know T1, we need to know T2, we also need to know the initial velocity, we also need to know the final velocity before we can resolve T2 by T1 and V by T by V by T by V by U rather. So for upward motion, we will obtain T1 and also the initial velocity, because if you look at the part we have drawn here, we have U, and we can also have T1, which is the time of the object while it was in this upward motion. So therefore, we use equation of motion to resolve all of this. One of them is where we have final velocity equal to initial velocity plus acceleration multiplied by time. If we look at this very well and align it with what we have on ground, So we can say that this v corresponds to v1, which is the final velocity while the object was on the upward motion, and it is equal to u, the initial velocity, plus this acceleration here. This acceleration here is obtained up, so which is a1, that is a1, and then multiply by t. Let's say that t now is t1. Okay, so this v1 is equal to 0. We have said that while the object gets to the highest point here, it will stop temporarily before now coming down. Therefore, we can obtain from here t1 equals to v or equals to minus u, t1, yeah, equals to minus u divided by a1, but we can re-express it minus u, first u divided by, what is a1? A1 from here is minus f by m plus g. So this can go. So we can now have t1 to be equal to u divided by f divided by m plus g. So this now gives us the t1, but we still need to resolve what this u is. So we can say this equation is equation 2. Let's take it to be equation 2. And so again, using the formula v square equals u square plus 2as, where s here is the distance from the point of projection to the highest point, which is h now, and then a is what we already know. A is what we know, that is a1, and then u is the initial velocity. That is what we want to see how we can replace here. Okay, so let's go on. This v is v1, we know it's 0, so it is equal to u squared, this is squared also, u squared plus 2, this is h, let's write h here, and then this is a1, let's substitute a1. A1 is minus, okay, so let's put the minus here. A1 is minus f over m plus g. So we have this, then is equal to 0 because v1 is equal to 0. So this implies that u square is equal to 2h into f by m plus g. Therefore, you can have u to be the square root of 2h into f by m plus g. So we can say this is equation 3. We still need it to resolve the u here. So therefore we can recalculate t1 to be equal to we substitute this in its place, which is square root of 2h into f by m plus g divided, maybe I should write it like this, divided by f over m plus g. Okay, so we can resolve this one and then find it to be 2h divided by f over m plus g. This we All right, let me write it this way. You can say square roots, sorry, this into f over m plus g. Yeah, that is what we have. Then this will be 1 over this, but it come into the square root, and then it gives us square. Have a thing like this. So when we have a thing like this, we can divide this to take 1 off here, so that we can have t1 to be equal to square root of 2h divided by f by m plus g. So we can note this one also as equation 4. For the upward motion, I think we have got two things, t1, which we will need here, and also u, which is this, which we need to resolve the question. We will consider the downward motion to obtain t2 and v, to address t2 and v. So how do we do that? We just follow the same procedure. So if we do that, let me give the schematic of the problem again. So this is like the downward motion, this is the final velocity. At this point, v1 is still the velocity, but it's 0. So you can use dotted line to show the other part, but we don't really need that now. So the height is still h from here to here. It's not different. It's h. The distance of the motion is still h. All right. So we can use this now to resolve whatever we need to resolve. First, the acceleration of the object while coming down. We still use the same second law, the mass of the body, square y, d square y, d t square. This stands for acceleration, is equal to the effective force acting on the object while it is coming down. So what is this effective force? Let us start from m. Acceleration now is a2 is equal to, there are two again. The first one is the weight of the object. The weight of the object is mg. It's actually in favor of the motion because it acts vertically downwards. So mg is mg, yes. And again, the second one is the resistance. Wherever the motion is going, the resistance is against it always. So it's still minus f. Let us write it this way. It's still minus f. So we have this equation, and then we can resolve a2 to be equal to, we have minus f over m, then plus mg plus g minus f over m plus g. I think it's cleaner to write it like this. Is equal to g plus minus f over m. All right, so maybe we call this equation 5. We also try to obtain t2 from the formula v equals u plus at, like we have done before. So final velocity here is v, sure, is v, is equal to u is now v1 and it's 0, and then plus, we now substitute this a now is a2. What is a2 is here, so it is g minus f over m, that is a2, then multiply by the time of a downward motion, that is t2. So from here you can as well say that t2, this implies that t2 is equal to v divided by g minus f over m. Like we did before, we need to substitute this v whenever we obtain it, How do we obtain it? This is equation 6. We obtain it from, let me still manage here. So how do we obtain that v? From v squared plus or equals to u squared plus 2as. Having this, like I explained before, this is the maximum height reached, that is h. This acceleration now, which is a2. Initial velocity v1 for downward motion, v is the final velocity. So v square is equal to u is v1 square plus 2a. A is here, which is g minus f over m, then h. This is 0 because v1 is 0. So that implies that v squared is equal to 2h into g minus f over m. And here we can find the square root of v. So that is v there. So we have square root of 2h into g minus f over m. Maybe we still call this equation 7. All right, therefore, we can now go back and find T2 properly, which is V, and then V is equal to square root of 2h into g minus f over m. Yes, and then use g minus f over m to divide it, just as here. So if we do that, we'll get T2 to be equal to 2h in square root into g minus f over m, yes, divided by 1 over this. So it's going into square root. It will become g minus f over m square. So we have it now to be 2h in square root over g minus f over m. Yes, this is what we have now. So we have all we need. We have, this is t, we have t1, we have t2, we have u, we have v. Therefore, we can now find t2 over t1, and that is equal to substitute t2. T2 is square root of 2h by g minus f over m. Now divided by t1. What is t1? It's also square root of 2h divided by f over m plus g. So finding the square root, we will then arrive at this expression here, which is the square root of g plus f over m divided by g minus f over m. So again, v over u is equal to v. What is v? V is square root of 2h into g minus f over m, and divided now by u. What is u? U is also 2h into f over m plus g. So therefore, when we resolve this, we have v over u equals to g minus f over m divided by f over m plus g. Yes, that's what we have, and so that's how to solve this particular problem. Thank you.